Physics students, good afternoon. Mr. Fugue here. Here in this video today, we're going to be looking at group problem 1, which covers over the concepts of vectors related to what we covered in Unit 1 in class. The group problem we'll be working through is also posted on our page on Canvas, so you can access it there. We'll be working through the steps to solve this problem here together. So I won't spend too much time reading through the background of the problem, given that hopefully you can access that on Canvas. Essentially what we're looking for here is to determine if we get a cell phone signal at various locations from a tower located here in Edmond. We are given some instructions for where the tower is located, as well as how to get from the tower to certain locations that we are looking at, namely Edmond North and then later on Lake Arcadia. So here, the first part A of our group problem, asks us to draw a picture of the situation based on the directions that we are provided. So I'm going to start with these directions up here. I'm going to just draw an arbitrary point and refer to this just as our cell tower. We can put it anywhere we want. I'll just choose a point and put it there. To get from the cell tower to north, our school, which is one of our locations of interest, will travel 1.3 miles south. We'll just say south is going to be down vertically here. 2 miles west, so we'll represent west as to the left. Then another mile south. And then finally 1.4 miles west. And again, our picture doesn't need to be perfectly to scale, just roughly so that it gives us an idea of the directions that we're going. And then that will end us over here at Edmond North, right? Now moving on, part B says we have many small vectors that we are going to combine into our overall displacement vector. Because what we're concerned with is what is the displacement from the tower all the way down to Edmond North, right? We want to know, do we get a signal from the cell tower out here, right? Cell signals don't necessarily travel down each of these streets. It's just going to move in a straight line from the tower to our location. But we're going to use these individual vectors, parts or components as we've called them, to find the overall displacement. So I'm going to combine the x components here. X's are going to be our horizontal components. So the two components west, that's 2 miles and 1.4 miles. So I will say overall, I'm going to add those together because they're in the same direction, and we travel 3.4 miles west. We can also call that a negative 3.4 miles. If we were thinking about this more in terms of an XY coordinate plane, left or west is negative. Either one of those is an appropriate way of identifying that direction. In the Y direction, 1.3 and 1 mile, those are both vertically downward or south. So I can combine them. We'd be traveling 2.3 miles south. Or if you want to represent this as negative 2.3 miles, we can do that as well. Either one is an appropriate way of representing it. Now once we've done that, okay, the next part of our problem is going to ask us to use those to find our overall displacement vector. So I'm going to pan down here just a little bit. And now what I'm going to do is I'm going to redraw those components. Okay? And I'm going to draw them tail to tip. So draw one, and then from the end of one, we'll draw the beginning of the next. So 3.4 miles west, or negative 3.4 miles in the x direction. And 2.3 miles south, 2.3 down, like so. And then we'll just draw an overall vector from our starting point to our ending point in a straight line. Now, because this is a right triangle, or mostly a right triangle, I haven't drawn it perfectly here, we can use trig functions to solve different parts of our triangle. We can also use Pythagorean theorem, which is what we're going to use here to find our hypotenuse. We can call this maybe part side C. This is A and B. We'll call the hypotenuse C. So here we go. A squared plus B squared is equal to C squared. In this context, it doesn't really matter what we call A and B. Those are just going to be the two component sides of our triangle. So we'll just call A 3.4 miles. Remember, even if we call this value a negative 3.4, when we square that value, our result will be positive. So 3.4 miles squared plus 2.3 miles squared is equal to C squared. Okay? So we'll plug this in real quick. We've got 3.4 squared plus 2.3 squared. That will give us a value for C squared. That's equal to, I get 16.85. And then to get c by itself, we'll take a square root of both sides of our equation. We'll get a value for c, our hypotenuse here. Should be a little over 4, yes, about 4.1 miles. That is part of our displacement. That's the magnitude, how far the cell tower is located away from north. Now we also need to find our angle here. Remember, our convention is that we always measure our angle relative to where we start. So we start up here at the tower and then work down to north. So here, our angle theta, we can use a tangent function because we know the sides that are opposite and adjacent to our angle. So tangent theta is equal to opposite, 2.3, over 3.4. I'm going to leave the units off here just to make this a little bit easier to work with. And then to get theta by itself, we have to get rid of this tangent function that is attached to it. And as we talked about in class, we can use an inverse trig function. So I'll kind of apply that inverse on both sides of our equation. So tangent and inverse tangent, those will cancel out. And what we left with, theta, our angle, is equal to the inverse tangent of 2.3 divided by 3.4. Now when we plug this in, we'll want to make sure we're in degree mode, otherwise we'll get an answer in radians, which we don't want for this problem. So we'll go second tangent, 2.3 divided by 3.4. We'll get about 34.1 degrees. So our angle theta